18.2 Formation and movement of glacial ice. Describe how glaciers move, the rates at which they move, and the significance of the glacial budget. Snow is the raw material from which glacial ice originates, therefore, glaciers form in areas where more snow falls in winter than melts during the summer. Glaciers develop in the high-latitude polar realm because, even though annual snowfall totals are modest, temperatures are so low that little of the snow melts. Glaciers can form in mountains because temperatures drop with an increase in altitude. So even near the equator, glaciers may form at elevations above about 5,000 meters, 16,400 feet. For example, Tanzania's Mount Kilimanjaro, which is located practically astride the equator at an altitude of 5,895 meters, 19,336 feet, has glaciers at its summit. The elevation above which snow remains throughout the year varies with latitude. Near the equator, this boundary occurs high in the mountains, whereas in the vicinity of the 60th parallel, it is at or near sea level. Before a glacier is created, however, snow must be converted into glacial ice. Glacial ice formation. When temperatures remain below freezing following a snowfall, the fluffy accumulation of delicate hexagonal crystals soon changes. As air infiltrates the spaces between the crystals, the extremities of the crystals evaporate, and the water vapor condenses near the centers of the crystals. In this manner, snowflakes become smaller, thicker, and more spherical, and the large pore spaces disappear. As air is forced out, what was once light, fluffy snow is recrystallized into a much denser mass of small grains having the consistency of coarse sand. This granular recrystallized snow is called firn, and is commonly found making up old snow banks near the end of winter. As more snow is added, the pressure on the lower layers gradually increases, compacting the ice grains at depth. Once the thickness of ice and snow exceeds 50 meters, 165 feet, the weight is sufficient to fuse firn into a solid mass of interlocking ice crystals. Glacial ice has now been formed. The rate at which this transformation occurs varies. In regions where the annual snow accumulation is great, burial is relatively rapid, and snow may turn to glacial ice in a matter of a decade or less. Where the yearly addition of snow is less abundant, burial is slow, and the transformation of snow to glacial ice may take hundreds of years. How glaciers move. The movement of glacial ice is generally referred to as flow. The fact that glacial movement is described in this way seems paradoxical. How can a solid flow? The way in which ice moves is complex and is of two basic types. The first of these, plastic flow, involves movement within the ice. Ice behaves as a brittle solid until the pressure upon it is equivalent to the weight of about 50 meters, 165 feet, of ice. Once that load is surpassed, ice behaves as a plastic material, and flow begins. Such flow occurs because of the molecular structure of ice. Glacial ice consists of layers of molecules stacked one upon the other. The bonds between layers are weaker than those within each layer. Therefore, when a stress exceeds the strength of the bonds between the layers remain intact and slide over one another. A second and often equally important mechanism of glacial movement consists of an entire ice mass slipping along the ground. With the exception of some glaciers located in polar regions where the ice is probably frozen to the solid bedrock floor, most glaciers are thought to move by this sliding process, called basal slip. In this process, meltwater probably acts as a hydraulic jack and perhaps as a lubricant that helps the ice move over the rock. The source of the liquid water is related in part to the fact that the melting point of ice decreases as pressure increases. Therefore, deep within a glacier, the ice may be at the melting point even though its temperature is below 0 degrees Celsius 32 degrees Fahrenheit. Other factors may also contribute to the presence of meltwater deep within a glacier. Temperatures may be increased by plastic flow, an effect similar to heating due to friction, by heat added from earth below, and by the refreezing of meltwater that has seeped down from above. This last process relies on the fact that as water changes state from liquid to solid, heat, termed latent heat of fusion, is released. Figure 18.7 illustrates the effects of these two basic types of glacial motion. This vertical profile through a glacier also shows that not all the ice flows forward at the same rate. Frictional drag with the bedrock floor causes the lower portions of the glacier to move more slowly. Smart Figure 18.7 Movement of a glacier. This vertical cross-section through a glacier shows that movement is divided into two components. Also notice that the rate of movement is slowest at the base of the glacier, where frictional drag is greatest. Tutorial. Glacial movement. On your browser.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the two main causes of glacial movement. So glaciers move, and if you want proof of that, here's an interesting experiment that was done in the Swiss Alps on the Rhone Glacier. Basically, they strung a line of little pegs across the glacier and then came back 8 years later to see where those pegs were. And they found that the pegs had moved to new positions. Some of them had moved by a relatively small distance, only around 320 meters, and others had moved a greater distance, more like 920 meters. So why was this? We can take a look by examining this cross-section of a glacier. We'll notice that in the upper part of the glacier, there are a bunch of crevasses. This is called the zone of fracture, and if you're ever walking across a glacier, you've got to be very careful when crossing crevasses because they are deep, but not too deep. They only extend down to a certain depth in the glacier, only around 150 feet or around 50 meters. And beyond that, they pinch shut, and below that, the glacier is pretty much solid ice. So to consider how the glacier moves, let's consider this starting point here, this line that we've just drawn here in the glacier. From that point, we end up seeing that the glacier moves partially by sliding. So the actual glacier itself slides as a solid mass over the bedrock underneath it. But in addition to that, the glacier is also flowing. So there's an additional component of internal flow, and that internal flow is less towards the bottom of the glacier and greater towards the top of the glacier, although of course the zone of fracture doesn't flow at all. So when you add the sliding to the internal flow, you get the total movement of the glacier. Most of it comes from internal flow. So where does that leave us in terms of the pattern that we observed here on the Rhone Glacier? Why do we see some of the markers have moved a greater distance as compared to their neighbors? All right, so you had a moment to think about that, and probably if you've had the glacier chapter of the textbook after the river chapter of the textbook, then you already have a sense of why this answer would be true. Basically, the velocity is greater in the middle of the glacier towards the top because that is the point that's furthest from frictional drag in terms of the ice scraping against the rock on either side. So just like a river, you would see that the greatest velocity is in the middle and the least velocity is towards the edges. Thanks very much for your attention. This has been another Smart Figure.
Eye on Earth 18.1. The central focus of the satellite image is Bert Glacier in Antarctica. In this region, the glacier advances at a rate of about 0.8 km, 0.5 mile, per year. Take note of its position in relation to other labeled features. Photo by NASA. Question 1. Is Bert Glacier flowing toward the top? In contrast to the lower portion of the glacier, the upper 50 meters, 160 feet, or so are not under sufficient pressure to exhibit plastic flow. Rather, the ice in this uppermost zone is brittle, and this zone is appropriately referred to as the zone of fracture. The ice in the zone of fracture is carried along piggyback style by the ice below. When the glacier moves over irregular terrain, the zone of fracture is subjected to tension, resulting in cracks called crevasses, figure 18.8. These gaping cracks may extend to depths of 50 meters, 160 feet, and can make travel across glaciers dangerous. Below this depth, plastic flow seals them off. Figure 18.8. Crevasses. As a glacier moves, internal stresses cause large cracks to develop in the brittle upper portion of the glacier, called the zone of fracture. Crevasses can extend to depths of 50 meters, 165 feet, and can make travel across glaciers dangerous. Photo by wave/glow images. Observing and measuring movement. Unlike the movement of water in streams, the movement of glacial ice is not obvious. If we could watch a valley glacier move, we would see that, as with the water in a river, the ice moves downstream at different rates. Flow is greatest in the center of the glacier because the drag created by the walls and floor of the valley slow the base and sides. Early in the 19th century, the first experiments on glacier movement were designed and carried out in the Alps. Markers were placed in a straight line across an alpine glacier, and the line's position was marked on the valley wall so that if the ice moved, the change in position could be detected. Periodically the positions of the markers were recorded, showing the movement just described. Although most glaciers move too slowly for direct visual detection, the experiments successfully demonstrated that movement nevertheless occurs. The experiment, illustrated in figure 18.9, was carried out at Switzerland's Rhone Glacier later in the 19th century. It not only traced the movement of markers within the ice but also mapped the position of the glacier's terminus. Smart